Howdy! Today we are going to be building a physically modeled tape saturation plugin. It has some realistic tape hysteresis for super chunky tape style saturation, and we're going to be doing this all from scratch in Max for Live. But first, let's check out what it sounds like. So here's a dry drum loop. You can see it's peaking just over -1 dB. It's also hitting about -12.5 LUFS. In this demo, I have some gain compensation so that we're always hitting the same peak level. We can hear how much loudness we get for the same amount of headroom with this tape saturation plugin. I will also be showing you what the dry signal sounds like with a pre-emphasis filter, and then what it sounds like when we have this dry signal go into the pre-emphasis filter and then into the tape saturation, which is kind of a standard way of recording to tape. So let's hear all four of those chains back to back. So you can see same headroom, much louder, also sounds chunkier, crispier. Let's just hear the dry signal and then the tape with emphasis back to back. So to implement this from scratch, let's first drop a blank max audio effect on our effect rack. Now we can just delete everything and replace it with mc.plugin and mc.plugout. And this just gives us one wire we have to deal with. And then we want to oversample our plugin. And the way we want to do this is with mc.poly. And then we give the name of our patcher, which we want to upsample. So first we have to create a new patcher and create in_1. We'll just connect this right to out_1. And now if we save this somewhere that's in our max path, I'll just overwrite this tape poly. Now we can call this over in our main patcher. We can say tape poly and then 2, which will run 2 instances in stereo. And then we say up 16, which will upsample by 16. And these are those inlets and outlets we just created. So if I connect this now I can just test that audio is coming in and out. So you can actually test that your upsampling is working by opening up this upsampled patcher and putting in a sinusoid above your Nyquist frequency. So I can do that by typing cycle tilde 55 kilohertz, which is well above our Nyquist of 24 kilohertz. And if you connect this to the output, you get silence. If you were to try this without the upsampling, you're going to get aliasing and you'll have a really high ringing pitch. I'm not going to do that here, but feel free to try it yourself if you don't believe me. Cool. And this 55 kilohertz sine wave isn't just to demonstrate the oversampling. This is also part of our final plugin. This is going to be our bias signal, which linearizes the saturation. So it doesn't make it totally linear, but it removes some of the harmonics generated by our plugin the more of this bias signal you have. And we probably want a knob to control that bias amount, but for now, just to keep it simple, I'm just going to do a constant attenuation of 0.1 before combining it with our input. The next thing I want to do is create a gen tilde patch, and I'm going to call it something like tape hist or something. And this is where we are going to send our input combined with our biased signal. And the output's going to go here. So this tape, the reason I want to do this in gen is because gen, if I make this bigger, gen has this code box feature. And now inside of our gen patch, the way we use code box is just by double clicking and then typing code box, and it brings up this little box where we can write C-like code. And for like really long math equations, it's going to be way easier to type it in than to draw it out with the kind of classic max wires. So the way we use this code box is by connecting in one to out one, but we're going to need to do a whole lot of coding before this will become usable. The first thing we're going to do is create some helper functions. So the first is a derivative, and the input is going to be t, which is 1 over the sample rate. X of n1 means the previous x, the last sample of x. Xd of n minus 1 means the derivative we estimated for the last sample. And then we use these little curly brackets in max to create a function, and we return 2 sets of parentheses and then 2 over t, and then we multiply that by x minus x of n1, and that whole thing we subtract by x, the derivative of x n1. And then you need to put a little semicolon after lines of code. That's just how CodeBox works. The next two functions are called Langevin and Langevin prime. So we'll just say are snippets of the main differential equation that we want to implement. So we'll just do that. It makes the ending code look cleaner, I guess. So Langevin just has one input x, and then we have the little curly brackets again, and then we just have to write some code. It's going to be t1 equals 1 over tan h of x, t2 is 1 over x, and then our output y is equal to t1 minus t2. But it's not quite our output. Well, it is, but it isn't. What we have to do is check if this output is going to be stable. So what we do is we check the absolute value of x, and we check if that's greater than 0.0001. And basically just this equation up here is not stable for values lower than that. So what we do is, if it's not stable, and the way we write this is stable, it's kind of like asking like stable question mark, and if it is, we return y. Otherwise, we just return x over 3, which is like close enough to the Langevin, but it is stable for values smaller than this. Langevin prime is the next function I want to create. It also just has an input x, and we're also going to first ask if it's stable. So is the absolute value of x greater than 0.0001? And I have to make sure I have semicolons on all my lines. I just missed one here. And then we similarly have t1 equals 1 over x squared, and t2 equals 1 over tan h of x, and this other value called t2 pow 2 is equal to t2 squared. And then our output is going to be t1 minus t2 squared plus 1. And then we return from this function, if x is stable, we return y. Otherwise, we return just a constant 1 over 3. And now we get to that actual differential equation. So we're going to call it Giles-Atherton because that is the name of the physics-based model. We can use this equation right here to get this tape-like behavior, this hysteresis loop out. And it's going to have a bunch of inputs. The reason there's so many inputs is partially just because of how CodeBox works. We need to also pass in these parameters. These are kind of like the physical parameters that describe our material, and they're just going to be the same every time. It's alpha, A, ms, k, and c. Let's write x equals, in parentheses, h plus alpha times m all over a, and L is equal to the Langevin of X, and L prime is equal to the Langevin prime of X. Then this variable we'll call mdiff is equal to ms times L minus m, and delta is equal to, if the derivative is greater than 0, it's equal to 1, and if the derivative is less than 0, it's equal to minus 1. So this is kind of how we're getting that state of if the tape derivative is increasing, we have one state. If the tape derivative is decreasing, we have another state. And then delta m is where we're going to get the sine of delta, and if that is equal to the sine of the magnetic, the mdiff, then our state is 1, otherwise it's 0. So this is where we get some more dynamic behavior. And then the denominator of our equation is equal to 1 minus c times alpha times, in parentheses, ms over a, and that's all times L prime. And there's some more variables. T1 underscore num is equal to 1 minus c times delta of m times m diff. T1 denominator is equal to 1 minus c times delta times k minus alpha times m diff. And then T1 is going to be equal to the T1 numerator over the T1 denominator, and then that's multiplied by the derivative of h. And T2 is equal to c times, in parentheses, m of s over a times h, the derivative of h, and times that L prime value. And then finally we can return T1 plus T2 over the denominator. If you were to go and compare this code with this equation, it should be the same thing. It should. We'll see. It's another hard thing about a complex video like this is we won't have much to test until the end. You kind of just have to, that's not totally true, but there's not a whole lot of things you could test with audio. We can't listen to this until we just finish implementing it. But we're actually almost there, believe it or not. We have some more easy helper functions, and then we're very close, I promise. So our next one is just helper to compute RK4 solver. So this is just one little part of the solver. It's kind of the weighted average, and the inputs of this function is the previous magnetic state, and then these K1, K2, K3, K4 values we get from doing the Runge Kutta solver. And the output of this is going to be m of n1 plus K1 over 6 plus K2 over 3 plus K3 over 3 plus K4 over 6. And this one, hey, it's simple. Let's check it. Let's make sure we got it right. It's actually manageable to see if we got it right. That should be this one. It's our previous m plus K1 over 6, K2 over 3, K3 over 3, K4 over 6. Hey, we almost got it right. We just forgot a semicolon. Cool. So these are actually all the helper functions we need, and believe it or not, we're almost done. Now that we've functionalized all the hard parts of the code, it's really easy to turn this into a tape model. So first, let me remind us the format of CodeBox. you define functions first, then you define constants, and then you can run your main code with inputs, processing, and outputs. So first, for constants, the way we do that is we write param with a capital P, and alpha 0.0016 is our alpha constant. We're going to have a param called a, which is 22000.0. And by the way, the reason I'm doing these as params, which means you can send messages to this code box to change these parameters. So down the line, you could, these constants are for like one type of tape machine that Chowdhury modeled, but you could change these to model other tape machines or even inductor coils or other things that have hysteresis. So our other constant is with the type capital param first, and then ms is 350.000.0. So don't forget your semicolons. And then param k 2700.0. Param c is 0.17. And that's all our constants. All right, and we're almost ready for the main code, but there's kind of one more thing I want to talk about. It's defining the previous state. So these aren't quite constants, but it's not quite the main code either. We're essentially initializing things called history items, and these are values within our code which we want to use when we're processing the next sample. So this is hn1, and then you do parentheses 0 semicolon. That means we're initializing it to 0. I'll make a comment. This is the previous magnetic field, in parentheses previous input. And then our history hdn1 0 colon, that's our previous derivative of magnetic field. And our history of m is our previous magnetization, which in parentheses, that's our previous output. Cool. So now we're ready for the actual main code. So our input is going to say, we're going to say h is equal to input 1. And I'll leave a comment. That's the magnetic field for the current sample. And then t is going to be equal to 1 over the sample rate. H of d is going to be our derivative of t, h of n1, the derivative, the previous derivative estimate, and that's it. And then here is our Runge Kutta solver. We do K1 is equal to T times the Giles-Atherton model we defined above of M of n minus 1, H of n1, the derivative of H of n1, and then this is what I was talking about. We just have to pass all those constants to that function each time. We'll look for typos later. And then I'm actually going to copy and paste this because the other ones are going to be kind of same, but different if you catch my drift. So we're going to swap out this value with m of n1 plus k1 over 2. And this one gets replaced with, in parentheses, h plus the previous h, hn1 over 2, and this gets replaced with, in parentheses, the derivative of h plus the previous derivative of h. And apologies, this one's a little overflowing, but I think to keep the screen big, we'll keep the code box this size. All right, and then for K3, once again, I copy and paste because it's very similar to the second line. We're just going to replace this K1 with a K2. Bing, bang, boom. We have our next line of code. Then for K4, I'm going to copy and paste this one, except this is m of n1 plus K3. You can kind of see each of these Ks, sorry, I have to rename this. Each of these Ks, they kind of always depend on the previous K. It's kind of how this works. And then we replace H of N1 with H, HD of N1 with HD. Man, we are almost there. I can taste it. So it's M, our current magnetic state. We go and compute it based off of our previous magnetic state, K1, K2, K3, K4. With that function, we defined M of N up here. And now we can set our output, first of all, is equal to M. And then we need to set up the history for the next samples. So up here, we define these history values, which kind of allows us to store some sort of like memory in this code. But what we got to do is basically say, like, tell it what the history maps to. So H of N1 is equal to the current H for like this round. But then the next round, it's kind of the previous H, if that makes sense. And then HD of N1 is equal to the current HD, and M of N1 is equal to M. And that's the code. Let's test this out. So we hooked this up. We can save this. We gotta save this as tape hysteresis. Sure. Tape hist. Before I run audio through this, I have to fix a couple of typos. This term down here should be HD of N1, and then on the lines for K2 and K3, I forgot to divide this term by 2. Now we should be good to go. Okay, so it's working, but I can tell you from experience, it's not working too well. And that's because the range of values is too small. Let me quickly show you an example of how we can test that this gain staging is off. So here's just a simple sine wave oscillator. And it's going into that tape plugin we just wrote, but we're still getting just a sine wave out. So what's up with that? Like I said, it's just the way that Max handles numbers. It maps audio. Even though it's almost clipping in Ableton, it's still a relatively small number in Max. And this is a physical model that expects those units for H to be like huge, like magnetic field numbers. So how we're going to do that, we're just going to do a quick and dirty hack. I mean, if we were actually developing a plugin, you'd want to control for this to control the drive. But just really quickly, I'm going to scale this number up by 90,000. And then, of course, we're going to need to scale back down so it's quiet once we're back in Ableton. Divide tilde 90,000. And yeah, let me just wire this up like this, like that. And then once again, moving both the bias signal and the input signal to scale it up. And now, there we go. So now when we turn this plugin off, sine wave, turn the plugin on, we're generating those harmonics. That's what we want. All right, we're finally ready to demo what this patch sounds like. I've pulled up a track I'm working on because I was getting a little sick of that noisy drum loop, and I've added a pre-emphasis filter to the effects chain, as well as some gain compensation so that when I disable and enable, we will get about the same amount of headroom as we can monitor with Pro L2, and then we can also check the loudness and then just hear what it sounds like. So let me mute my mic and we can check it out. it. So that's what this tape emulator Max for Live prototype sounds like. I'll give a link to download it in the description of this video, and you can let me know what you think. I don't know if it's any good, but I will definitely keep working on improving it. Yeah, so that's it for today, and I'll see you next time.